So today's topic is about embedded systems, and this is very short topic. It just introduces what kind of special things you need to take care of on the embedded systems, because you do not have MATLAB, you do not have computing power usually on embedded systems. In quite a lot of cases, you don't even have floating point numbers on the embedded system. But let's take a look at this core board. Okay, I took a look at the collaboration thing, and unfortunately some didn't score points at all because either didn't check the comment others exercises, or others couldn't comment their exercise, either or. Okay, but anyways, it was a fun exercise. I will be using that one in future. Otherwise, as you can see, we are closing the end. After this lecture session, I'll go through all the groups and make sure that everyone has a project topic and that you can actually start working on the project. I already brought some stuff for one group for doing the project, but we'll see. And now I just need to start, since otherwise I'm a little bit afraid of my voice this morning. So, embedded systems, what kind of considerations we need to take on the into account? Okay, about the performance. First of all, what takes time in digital signal processing is that it actually is processing continuous kind of signals. So basically what you need is horsepower to do it all the time. Unless you are post-processing the data, but most of the systems actually are doing it in real time. Okay, and when you're taking a look at the simple FIR system or any system overall, if you do a filtering, it basically, you calculate for each output signal, you basically calculate a product of input signals and then sum of products of the history of output signals. Okay, so plenty of operations, and most importantly, there's just about same number of additions and multiplications. Okay, and that has even a own name. It's multiply, accumulate operation, MAC. So if in digital signal processing you see a term MAC, it's not about your local MAC address of a system, but multiply, accumulate operations and how fast you can do those. The digital signal processors usually say how many multiply, accumulate operations it can do at certain accuracy. Okay, and then there's a short code how to do it. So it's basically, on that display, it's basically a short part of code that could calculate the FIR system, one small block of it basically. So you have the pointers, data pointer, and data pointers for input data and output data, and then you just calculate for each output you will add a product of the this what is it? The filter coefficients times the input signal. Okay. And do some housekeeping. Another thing, okay, speaking about the experience, you don't know how easy it is to make a core dumps on signal processing. Since you quite easily start reading from illegal sections of memory, and then the program crashes. In good old times, the whole system crashed because of that, but not too much of that kind of things, as long as there's a operating system, a decent operating system. Okay. And how long actually Mac operation takes? It varies a lot. Every single microcontroller or microprocessor core has different kind of architecture, and they may have floating point units on them, and then the arithmetic logic unit has probably different width that you can use either, say, just 16-bit ALU, or you can divide it into two 8-bit ALUs. So it's widely depending on the processor architecture. So practically what it means that when you are taking designing a signal processing system, you fundamentally first have to decide about the processor, and then you will just live with that decision. Okay. Okay. The floating point implementation. Floating point, we have been using double precision floating points. On MATLAB, it uses double precision floating point unless you say it otherwise. You can force a data also to be integer or fixed point, or a float, meaning the single precision floating point number. But on overall, these processors are generally optimized for these fixed point or integer operations. So ALU is done that way unless it's designed to do otherwise. There are some floating point processors. You can find it, for example, from the graphic acceleration cards for the highest performance. Okay, there you need actually this polygon kind of signal processing there in 3D or 4D. There you need a lot of computing power, and you don't want to spend time doing the floating point arithmetic with fixed point logic. Okay. The modern processors usually have a separate multiply accumulate unit, just because, well, signal processing is used in quite a lot of applications. Embedded systems controllers usually have, unless they are 8-bit, and even some of them actually have. Okay, you can do the multiplication. So addition is usually quite fast. Maybe in your, what is that? Digital technology, or digital circuits, or some other courses you already have done hand calculations of fixed points or integer numbers, maybe, or 8-bit, 16-bit integer numbers. Okay, so But anyways, the multiplication is usually the one that gives more trouble. And basically, there are two ways to do multiplication. One is by, of course, the hardware. That would be optimal. So if you are more powerful processor, say 16-bit or higher processor, they usually have hardware acceleration for floating point. But then it could be just single precision floating point, not guaranteed to have double precision floating point. On the other hand, this would be fast, but it's expensive. It's expensive to implement. It takes a lot of gates to make a floating point multiplication hardware. So it takes actually quite a large portion of the silicon chip, which means it usually doubles the price of the processor. Okay, that's why it's not guaranteed to have hardware support for floating points. But anyways, you can always do it by software. Okay, but while this is usually just, say, few clock cycles. If you do it by software, of course you can do the, even with 8-bit processor, you can do floating point arithmetics if you have time to do it. Single precision floating point multiplication by two numbers generally take about 200 instructions. And each instruction is 5 to 11 clock cycles. So we can say this is slow, sluggish, and thousands of clock cycles. Okay. However, if you have the sampling rate, say, few samples a second, you have all the time available, even with that slow software implementation of multiplication. It's always depends on the application, which way to go. Or if you are using some cloud services, meaning the server does the calculation, then even a small system can do the filtering. Just sends it into a filtering service. That would be actually a nice exercise for someone. Make an embedded system that takes in integer data, throws that to some server which does the filtering in floating point arithmetics and sends it back. I have no idea where to use it, but proof of concept. We are looking for proof of concepts on the on these projects. Okay. Then also, when you do the multiplications, one issue is also so-called fused multiply add. So how to speed up the multiplication with less silicon area. That's actually when you don't start not caring about the least significant bits. That's so-called fused multiply add. So you have the floating point multiply accumulate circuit, but it doesn't do much of the rounding other than so-called single cycle. It's usually it just cuts the result, cuts the bits. That's what I'm talking about here. With fixed point arithmetic, if you have, for example, 8 bits multiplied by 8 bits, you always get the product is actually, it's 16 bits. You have done multiplication with the 8-bit numbers, right? It gives you a 16-bit result. So the question is, how do you actually take the correct 8 bits, since what you want to have is the same size word length for the output as for input. Okay, so there is some room for the rounding. If you do the rounding at all, you could actually save some space by doing just starting from 6 bits on one and 6 bits from another one, and still get about the correct kind of results, or get the data as 8 bits, but then the coefficients only 6 bits, sometimes even 4 bits. This kind of things are actually quite usual on FPGA filter design, since you can make also FPGAs to do the digital filtering. Okay, how many of you have taken the programmable logic circuits at some point? Nobody? No one knows anything about FPGA circuits or VHDL? Okay, VHDL, okay. Good, yeah. Same thing, more or less same thing. All right, so, and yeah, of course, then there's a special category called digital signal processors, which are designed to do really fast calculations. And they also have usually parallel processing, pipelining, to do the several MAC operations at the same time and in a flow. Okay. So all the nasty stuff from processors and what was that architecture called? Processor and system architecture, which you all love, right? Okay, so all the nasty stuff is usually in those digital signal processors, but they are fast. So if you think of how to process radar signals, real radar signals, they work in gigahertz area, and even for example, Doppler radar, you get megahertz signals, Doppler shifts, and you are basically nowadays they are using, sampling. Is it at 1/4 of the carrier frequency? So they do, say, a few hundred megahertz sampling of the data, and then they process it in real time in a digital signal processing matrix. Oh, lots of power. Yeah. And what comes out? Bad weather forecasts. But it's fun. Okay. So about the computing accuracy. What happens if we start losing some accuracy on the parameters? So these are 3 different cases when you have a blue is the floating point accuracy, double precision floating point for reference. So this is how you design it. Right. This far we have been designing only this MATLAB filters, which would have some trouble on real embedded systems. If you take just 16-bit accuracy, which is quite nice already, 16 bits, it's lots of decibels. Wait a minute, 16, 12 is 70, 16 bits is 96 decibels, right? So 16 bits more or less covers the what human can hear, the differences on the sound pressure. Okay. So 16 bits would be good for data, but if you start doing the with this kind of design, 16-bit arithmetics, you are starting to lose some accuracy. Okay, and you can see the accuracy lost right here, which means that the 3 dB point is not anymore 3 dB point. The previous, oh yeah. So it actually shifts the beginning of filter. Even worse when you go down to 8 bits. Well, I wouldn't do any audio with 8 bits. But anyways, the 8 bits filter coefficients actually would cause already, you will lose some gain. You lose some gain there. And then also, it's not anymore the same filter. Totally different filter. Okay, and then even worse. When you quantize IIR filter, which has a pole in just barely inside of the unit circle, it actually can jump outside, and you will have a nice oscillator. Unstable system. So the rounding errors can and will make bad things about your system. Okay, but there's a cure, of course. Otherwise, we would be this would be a very theoretical topic. Since, of course, there is one or another way to come over of those facts, since we cannot afford filtering only with the double precision floating point. Okay, one is actually have the combining the systems, and one is the cascaded system. This is very classical. So cascaded system means so if we have a first system like that, we can also, if that is, say, nth order, we can divide this one in subsections, cascaded subsections, which has the H1Z, H2, H3Z such that H1Z times H2Z times H3Z is still the same H of Z. Okay. Why we can do that? Of course we can. Well, remember the this form. Okay, that's done. The product form of H of Z. Well, Z minus ZK, Z minus PK. Okay. And you have the zeros and poles. For example, something like that. Okay, so there are zeros and poles. And we could take and start combining these or separating the systems so that these zeros and poles would be my H1Z, second order system. The second one would be, okay, these, H2Z, and the third one is the remaining. When you do that one, you actually increase the computing accuracy. How come? Okay. One way to think of this one is actually think of the, what is this? Is this Fibonacci triangle? Six, 4, 1, and then, and so on. What is the 100th line here? Start 1, then 100, then a lot. Okay. And this would be, if you think of, say, x squared, 2x plus 1, so on. Same thing. Z, z to the fourth, z to the third time 4, like that one. And these actually become the filtering coefficients. And think of, say, that not 100 line, maybe even 30. 30th line, I think that will be 60, maybe like that. At the middle, there will be very big number, huge number at the middle, compared to very small number on the end, on the same formula. Okay, so you multiply something with 1,000 and one, another you multiply with 1. And the error is actually, it's not relative error, it's absolute error on that calculation. Okay, so basically those small numbers will disappear from the calculations. And if you have small error on this big number, it cannot be compensated by, by the other coefficients here. Okay, so in that sense, it's better to start cutting the system, hacking it down to second order sections. So SOS, SOS, SOS. 1, 2, 3. Second order systems or first order system. If there is single zero and pole, then it will be single order. Okay, but anyways, that's one way of doing it. It's straightforward and it helps. On MATLAB, you can actually play with that one. How would the second order system help on the calculations, especially if you design, say, more than 8th order IIR filter, then it starts making big difference. FIR filters are not that sensitive for that error because, well, it doesn't move the poles. But on the IIR filters, you have the very sensitive the part on the feedback part. If you make a small error on feedback, it actually can start, the adding up. Okay. So that's one way of doing it, but also it's also possible to do the parallel systems, although it becomes a little bit tricky. So instead of a single system, you will basically divide into, usually, two systems which are parallel. And their H1z plus H2z would be H of z. Okay. If you started from here to there, you need to find the common denominator polynomials in complex plane. It's not easy, although there are also some tools to do the division. On the other hand, you already have done similar kind of things. So this is also one filter structure. So for example, if it's high pass and low pass filter, it's just the same thing. But anyways, this one helps on FIR filters. If you do it that way, then basically it starts to reduce the amount of noise on the system. Magic. Yeah, pure magic. All right. Okay, that's just basically the same thing there. Second order systems. Calculation errors can be minimized by dividing a system to second order systems. Okay, and let's see. There's a comparison. So blue one, actually there are three different filters again. Blue doesn't show up anymore since it's actually behind the red one. The green line actually shows up the what happens if I just take and the normal direct form filter structure. So that's the case one here. That one, a single system. But if I divide that, and 8 bits of calculation, computing accuracy. Okay, not much. But if I just divide that system into second order sections, I get quite nice. It almost matches my floating point precision system. Almost, not quite, but almost. Okay. So if you don't have floating point precision available on hardware, okay, my suggestion would be to go to second order sections, and you can still do the calculations with the lower precision. Well, okay. Philosophically, floating point numbers are not accurate. Only accurate numbers in the world are integer numbers. Okay, but this is just philosophy. Okay, and there's just another example. The previous, I think, was FIR system, yeah. And that's the even more dramatic difference on the in case of IIR. IIR. Okay. That's all for the lecture part, and the rest of the course is about project. Okay, but now we can stop the recording. Thank you for attendance.